Hello everyone. Today we are diving into a classical control system problem. We are looking at a second order feedback system. Our goal is to see how changing the system gain directly affects how the system behaves, especially whether it smoothly reaches its goal or rings like a bell before settling down. So over here is a problem overview. Here we are given an open loop transfer function. So g of x is equal to g over s multiplying the expression s plus 3, and you're having a feedback, unity feedback, h of s equals to 1. And our objectives are that you have to find the closed loop transfer function, to also find the minimum gain for the overshoot. And last, we are also to calculate the time period t for the specific gain.
So in finding the closed loop transfer function, we are going to first of all identify our forward path, and that has been given to us in the question, and that is t of s equal to g of s over 1 plus g of s h of s. Yes, and we are going to do a substitution. So for this, we've been given our unity formula, which is h of s to be 1. So we are going to substitute that into our formula. We have g over s bracket s plus 3 all over 1 plus g over s bracket s plus 3, and finding our transfer function over here, we get our final result to be g over s squared plus 3s plus g.
Okay, so for part B, conditions for the overshoot. For the theory, we have overshoots occurring in an undamped system. So we know that the conditions, we have 0 to be less than zeta and also less than 1. Then the critical point, damping ratio must be less than 1. So from the diagram, we know that the overshoot occurs when the output of the system exceeds its desired steady state value. So since this is an underdamped, we have 0 being less than zeta being less than 1. So the system responds quickly, but it overshoots the target, then oscillates around it before settling.
Okay, so in calculating for the minimum gain, which is G for the overshoot, we would compare our system, which is a second order system, to the general relation of the second order system. So in comparing our characteristic equation, which is x squared plus 3x plus g is equal to 0, to the standard form, which is the general relation of the second order system, we know that the formula is x squared plus 2 zeta omega n s plus omega n squared is equal to 0. So now doing the comparison, we could tell that zeta n, which is the natural frequency, is equal to the square root of the g. But then before we would even get the square root, from the general relation itself, we could tell that the natural frequency squared will be equal to g. So now taking the square root of both sides, we would have the natural frequency, which is the omega n, to be equal to g. And now comparing the s part of the equation, we would also know that 2 zeta omega n will be equal to the 3. So now, since we've already found for our omega n, we can move ahead and then proceed and then find our zeta from here. Thank you.
Calculating our minimum gain, given the parameters, we have the omega n to be the root of g, and assuming that the damping ratio, that's the zeta, is 0.6. Calculating it, putting into the formula, thus we know that the formula will be the 3 over 2 root g, which is, it should be less than 0.6. That's the assumed damping ratio. So changing subject, making g the subject, we know that g will be equal to 6.25, meaning that g, that's the minimum gain, should be less than 6.25, which will now give out what we want. Thank you very much.
Moving on to the first part of part C, where we are supposed to calculate for the doubled gain. Since we already know that our minimum gain is 6.25, calculating for the new gain would be 2 times the value of the minimum gain, which is 6.25, and this should be giving you 12.5. So because the value of the new gain has changed from 6.25 to 12.5, it means the value of the frequency would also change. So you would be getting a new frequency. And in 10, we would also be getting a new damping ratio. So our new frequency, which is omega n, will now be the root of 12.5, which is the new gain value. And we should be getting 3.535 rads per second. And then for the new damping ratio, which is zeta prime, you would be getting 3 divided by 2 times the new frequency. And we should be getting 0.424 for the new damping ratio. Thank you.
Okay, so before determining the time period t, we first calculate the damp frequency. The damp frequency represents the actual frequency at which the system oscillates when damping is present. Because damping dissipates energy, the frequency is always slightly lower than the natural frequency. From our calculations previously, we've determined that the natural frequency is 3.53 rads per second. So, and then our damping ratio is 0.424. So to find our damped frequency, we use the standard relationship, which is the natural frequency root of 1 minus the damping ratio squared. If we substitute the values, we arrive at the answer 3.197 rads per second, which is approximately 3.2 rads per second. Thank you.
In the analysis, we explored that the feedback control system with the open loop transfer function and the unity feedback, we derived a closed loop transfer function, which allowed us to understand how the system responds to changes in the gain.
Okay, so our final time period, which is t, is given as 2 pi over omega d. So if we are to do the computations, we will get to know that the period is equal to 2 pi over 3.20. So now if we input these values into our calculator, we are going to get our final time period, which is t, to be equal to 1.96 seconds. Thank you.
So in summary, adjusting G allows us to control both energy and damping in the system, which is crucial for achieving the desired performance in the feedback control systems.
We were asked to find the closed loop function, which we derived as g over s squared plus 3s plus g. We were asked to find a minimum gain, which we derived as 6.25 with a damping ratio of 0.6. In further computations, we had our new damping ratio to be 0.42, leading us to damped frequency of 3.2 rads per second, eventually leading us to our time period, which was the main thing we're supposed to find, as 1.96 seconds. Thank you.